Problem number 2. Inside of a funnel of height 10 inches has circular cross sections as shown in the figure to the right. At height h, the radius of the funnel is given by r equals 1/20 of 5 plus h squared. The units of r and h are given in inches. The funnel contains liquid. This is not a cone, okay? Not a cone. You are not allowed to assume any sort of geometric shape out of this that isn't actually specified for you. Funnel contains liquid draining from the bottom. At the instant when the height is 3 inches, the radius of the surface is decreasing. So the radius of the surface is decreasing. That means dr dt equals negative 1/6 inches per second. At this instant, what is the rate of change of the height of the liquid? So we're looking for dh dt at h equals 3. The way you got to go about this is understand that I'm looking for some sort of relationship between r and h, not volume. I don't have to include volume in this one. The relationship between r and h cannot be any easier than what was already given to you. So if r equals 1/20 5 plus h squared, and I have to take the derivative of this, I end up getting dr dt equals 1/20 times 2h dh dt. If I plug in the two things I know, I plug in dr dt and I plug in h equals 3, I will eventually come down to dh dt equals, that would be negative 5/9 inches per second. The points here come from taking the derivative of r and then having the correct answer after plugging everything in. Part B. The base of the cylindrical tank with an open top has a radius of 10 inches. It's helpful because that means it's a constant. This will always be 10. And a depth that's modeled by x. So however much water there is in here, that depth is x. Assume the liquid is drained from the funnel directly into the tank. So that means dV dt is now it's positive 120 because it's draining into the tank. So that means the volume is increasing inside the tank. At what rate is the depth of the liquid changing? So we're looking for dx dt. So now what is the relationship between V and x? Or V and the height? If this is a cylinder, volume equals pi r squared times height. But since height for us is represented by x, we're going to have to use x. We cannot use h. We will take the derivative. dV dt equals 2 pi, wait, we will not take the derivative yet. We have a constant which we need to plug in. That way we avoid any sort of quotient rule or product rule or chain rule. V is equal to, if the radius is always going to be 10, 10 squared is 100, this becomes 100 pi x. Now when I take the derivative, it's not only easier, it's less rules. dV dt equals 100 pi dx dt. I plug in dV dt from over here, and I solve, so I get 120 pi equals 100 pi dx dt. Therefore, dx dt equals 6/5 inches per second. Here the units are pretty basic. 1 point for the derivative, 1 point for setting the derivative, or plugging in 120, and 1 point for the answer. there's a bonus point that comes up from A and B, and that bonus point is you have to have the correct units in A and in B, which are both inches per second, in order to earn one additional point. So far we had 2 in part A, 3 in part B, and the additional point, so 6 points total. Part C, at the same instant and from part B, so things that we know from part B is that the volume is not changing, and that dx dt is 6/5 inches per second. At the same instant, at what rate is the surface area of the water changing that it's in contact? The only part of the water that's in contact are the walls plus the base. The surface area of the walls is going to be the cylinder times the height. 2 pi r times the height, x. The base will be pi r squared. Again, r is a constant. R is 10. So we have 20 pi x plus 100 pi. If I take the derivative, I'll get dA dt equals 20 pi dx dt, and then this is a constant, so this turns into 0. I need to plug in dx dt, which is 6/5, and if I plug in 6/5 and multiply by 20 pi, I will have 120 divided by 5, or 24 pi. Now this will be inches squared per second, because it's the change in area over time.